Yeah, you can email to me, share it through Google Drive. Any of those options would be just fine. Okay, it should work just fine. Yeah, you bet. Well, welcome back, everyone. I hope you all had a great Labor Day weekend. Any questions before we start off today? Okay, the good news is it's a 4-day week as far as this class, or 3-day week as far as this class is considered. So I don't have a ton of topics for us to get through. We'll mostly be going through chapter 3. We may not finish it. We'll see where we end up. But for the announcements of the day, quiz 2 is due today. And well, I think that's really the major announcement. Any other questions so far before we get going? Okay, maybe the other thing I should talk about, since we are getting closer to that date, exam 1 is essentially 2 weeks away from today, except that it's on a Monday. So just 1 day shy of that. But what's going to happen on exam 1, and I'll notify the class when it does happen, is getting towards this weekend, probably on Thursday if I'm a little bit more caught up. I'm going to add the coverage for exam 1. We'll say exactly what sections you should be ready to go with, prepared for the exam. I'll include the allowable materials, things like calculators, the page of notes, scratch papers will be detailed here. And I'll also be adding the sample exam problems that we discussed as well. So you'll see that this section is going to transform probably Thursday, maybe Friday, if I'm a little bit behind. So that's where we're at so far. And I think exam 1 is pretty much going to cover chapters 1, 2, 3, possibly a little bit from chapter 4, but I'm not going to try to make it too big. Well, any other questions, folks, before we get started? Okay, well, we left off on section 3.1. We used the TID4 calculator to just show really quickly how to input data and do some computations. In chapter 3, we'll be using this calculator quite a lot. So if you have it with you today, it'd be a great idea to pull it out so you can practice along with us. So let's take a look where we left off. In 3.1, again, we calculated the sample mean and a sample standard deviation of these data. It was really just a preview. We're going to do that all over again in section 3.2 and do it in a careful way. But the idea with chapter 3 is it's nice to have a graph with all of our data, histograms or bar charts to explain what the interesting relationships are, where the data is concentrated. But when we just have graphs, we now have the uncomfortable idea of where is the data concentrated. We just sort of pointed at it and said, about here is where the data is centralized. To say how spread out the data was, we just said it ranged from a lower value to an upper value, but we would like to be much more precise. So in the calculator, this is the central value for symmetric data, the sample mean X bar, and this will tell us how spread out the data is. That's the standard deviation. But this is only if our data is symmetric enough. And that's about what's really going on in 3.1. When it says selecting appropriate numerical summaries, it's going to depend on the shape of our data set, whether it's skewed or symmetric enough. So let's get started with our first set of definitions. This was the first page of notes, but I kind of scooted it down here so we could do that initial example. First, we want to take a look at measures of center. Always think of center as where data is consolidated or concentrated around. Our author says measures of center describe where the data distribution is located along the number line, and it provides information about what the typical observations would be. The ones we're going to see for measures of center might be X bar. Think of this as the average. We'll usually say sample mean more often than not. I'll put here in parentheses, average. But if our data is bad enough, we mentioned we just can't use that. It gets moved in the direction our data is skewing. In fact, let's take a really quick visual just to tie that idea together. In section 2.3, we had some really gnarly looking data right here. The typical value we pointed to be right about there, but that's not where the mean is. The mean is likely further to the right because we're dealing with right skew data. So if we have badly asymmetrical data like these, we change from the sample mean to something else, uppercase M, which is the sample median. And instead of saying sample median, you could just say the 50th percentile. We'll see that word percentile here and there, especially coming up in section 3.3. But essentially all it's saying is half the data or 50% of the data should be lower than the number m, and half the data should be above that number m. So that's what we'll measure the center. And next we need to look at variability. Any questions at the moment? Okay, variability is just as important as knowing where your data is centralized at. When we say variability, we might be talking about something that looks like this. A lowercase s. Try to make it not look like the number 5. I struggle with that personally. The lowercase s is the sample standard deviation. And when we did our preview of computation, that's what was being calculated right up here. That SX is that sample standard deviation for that really simple data set we took a look at. So again, we have a problem with our measure of variability. Sometimes the variability standard deviation does really, really great. But if our data is terrible, if it doesn't have the right shape, we can't use it. We have to use something else. And we'll call it this. IQR, which stands for the interquartile range. We should also say, what in the world does that mean? That's a strange acronym, a strange word. Interquartile range is now saying, it's trying to say how spread out the data is, and it measures the distance for the central 50% of our observations. So that's what our interquartile range is going to measure. If our interquartile range is a large value, say 100, that means half of observations range from one value to another value at length 100 between each. If it's, say, interquartile range is 2, then half of your data set is constrained within a region only of width 2. We'll calculate each of these values in turn, but the first thing we have to do in this section, like we mentioned, is depending on the data, which statistic do we actually use? And we just put 4 on the table, which gets a little bit confusing. This example here in this table is just meant to be a one-stop shop where you can come back to and decide what is the right situation or right statistic to match the situation. But any questions first, folks, with our 4 statistics that have made a comeback here? Yeah.
Can you just for people
Yes, absolutely. In fact, that's kind of what this table is going down here. So let's do a really quick rundown. X bar, use that if you have symmetric data, and M if your data is absolutely skewed. And same pattern on this one. S is going to be for symmetric data. IQR is going to be for data definitely skewed. But then we'll run through it as a table as well to represent it. Other questions so far? Okay, part of the table is also just practicing those kinds of shapes once again. When it says shape of the distribution, I think I want to add just one extra set of words here. Let's say at least roughly symmetric. I'm going to put that in red because it's a quick edit out of nowhere. But it's a reminder that when we go to use or choose these different versions of statistics, we are forgiving the symmetry. We wait till things are badly skewed enough before we decide, yes, it's absolutely skewed in the right or the left direction, and we need to change our statistics. But we can highlight this in blue, this in green for center and variability. And if our data is at least roughly symmetric, it might look about like this. So here's my really fast histogram on roughly symmetric data. I'm going to force it to be skewed just a little bit to the right. I might make that skewing kind of borderline by putting in just an extra set right here. Now it's looking a little too skewed to even my eye. But if it looks like this, we've got a right skew to that. It's not horrible. We might be able to make it even slightly more right skewed, but that's definitely at least roughly symmetric. This is a situation where we would use X bar, the sample mean, to describe the center, and we would use S, the sample standard deviation, to describe the variability or how spread out the data actually is. So that's the situation for those two statistics. Again, keep in mind, this is the ideal situation. When things get too badly skewed in either the left or the right, we use different statistics and we have to use different statistical methods, making all of our conclusions a little bit harder. So let's just draw a couple rough skews. I'll show one to the left, one to the right. So something skewed left could look about like this. This would be my attempt to put something that is just absolutely horrendously left skewed, with some rather substantial outliers as well going off to the left. These are your data. X bar doesn't measure the center anymore. It's moving towards the left. And it gets even worse. The variability is a formula based off X bar, the sample mean. So that one's ruined too. We can't use either one of those statistics. That's okay. We can change our methods. Use M, the 50th percentile. It still does the good job. In fact, we all played an experiment right here. That's about where M really is in that location. Visually, it just looks like the center on a histogram for the median. And this strange thing, which we will see how to calculate in section 3.3, interquartile range, measuring the length of the central 50% of all observations. And I'm not sure why I put an extra row. I think I just want to draw another picture so we can focus on what skewed distributions look like. But if you're skewed, it doesn't matter if it's left or right. You use the median for the center interquartile range for variability. Does that make sense so far, folks, for picking those statistics? Okay, there'll be some questions in this section right out of WebAssign that's asking, based off of the data you might see or information you might know, what is the appropriate statistic to measure the center or measure the variability? It's really this idea right here that we're looking through in the table. But let's maybe just finish this off and put down something right skewed. I don't want to make this one too crazy, but just crazy enough so that I wouldn't call this roughly symmetric. If I make it go about like this, that's now looking pretty bad as a distribution. It's skewing to the right just a little too much for us to use nicer measures like X bar, the sample mean, S, the sample standard deviation. So that's our table on deciding how to pick some statistics. Any questions at all, folks, with what we have so far here? Okay, well, going off to our next problem. Here's where we're going to give this all a try. This is a problem we're going to build out our graphics from scratch, decide on what shape it has, and then determine what statistics we should really use. If we would like to, if we have time, I mean, we should have time, we just started. We might calculate those statistics as well, but that is really meant for the next section. So let me know how you feel about this problem. And we'll start off with a histogram would be great, but it's way, way too time consuming for us to do it by hand. So we'll go for a dot plot on these data. First, we should look at the context just to see what we're getting into. It says data on tipping percent for 20 restaurant tables is consistent with summary statistics giving in the paper. Beauty in the labor market evidence for restaurant servers are given below. So they didn't give us too much about this article other than the title. And here's all the observations. What I can tell you for sure is if you highlight something random, then this table tipped up almost 30%. So there looks like they're pretty happy with their service. This person was a jerk probably, or maybe something went terribly wrong with their order and it never got fixed. But those are all just tipping percentages. First thing we want is a dot plot. And again, for a dot plot, it's a good idea to think of the minimum value C, 0, and the maximum value, so we can capture everything. So it goes to a maximum, oh geez, I didn't see 105% on there. Could have been a mistake, or maybe that person was just really happy with their service. So we need to capture that minimum and maximum that I temporarily circled. I'll do a long horizontal scale Starting at 0, this is tip percentages. And now we just want to decide how many tick marks, or excuse me, how wide should each of the tick marks be? If we went in terms of 5, I'm looking at 20-ish tick marks. How about 10%? Does that sound all right to folks? Okay, it's always a judgment call, but if it was an exam question, I would print something else, something out like this, so we are not worried as much about those smaller matters. For quiz, we might have to do our own scale since we have that extra time. So I'm going to go by tens. 10, 20, 30, 40. And most restaurants, you should probably have all the observations around here, I'd say. But now it keeps on going. 50, 60, 70. Now we're up to 80% tip, 90% tip, a 100% tip. If I had a little bit more space, I probably would have gone 1 tick mark farther, but at least I can put a dot around 100. So I think this will qualify for a decent enough of a scale. Now this is the tedious bit, but I mean, it's our only second one and it has a possibility of being an exam question. So let's practice this one more time. We want to just take, in order to construct a dot plot, every observation and produce a dot based on it. So for this one at 0, I'll place a dot right here. We float it just a bit above the horizontal axis so that we can display the data itself and not worry too much about the graphics getting too compressed around here. Next, I have a value at 5, which I'll place right about here. And then it's just a matter of running through them. So I'll try to do this as fast as I can. You're probably already halfway done. At 45, I'm here. 32.8 places me about here. 13.9, right around 14. I have a 10.4, pretty close to around here. 55.2, about in the middle. I think something weird does happen with this one, so let's see where these values fall. I have 50 exactly here. That was a good tip. For row 2, I have a 10%, and this is where it does get interesting. Now, I plotted a 10.4 right about here, and my scale is not wide enough to really see a 10 relative to a 10.4. They just kind of overlap. When that happens on your display, we just put a dot right about here. Let me zoom in on this just to show how I did that. This one right here by the red dot, I moved slightly to the right because it was a 10.4 right there. And the one right at 10%, I try to put above the 10, but it's only slightly to the left. So sometimes we jitter one point a little bit to the right, one a little bit to the left to show where they are in reference to the horizontal scale, but we still stack them if they're very close, and the dots would overlap otherwise. Does that make sense to folks at the moment? Gotcha. And again, that's what's tricky with an exam. I'll print this scale on the exam because the way they stack is going to be dependent on how wide you made this in the first place. Okay, let's keep on going then. 14.6, some of your dots you might have to stack and just jitter to the left or to the right. And at 14.6, I think that's going to be one of them as well. I'll put it about here. They don't have to be placed perfectly, but as long as I look at your paper and to my eye, it's in the right neighborhood, I'm always going to be happy with it. Now I'm at 38.4, so closer to 40. 23 would be about right here. 27.9, just shy of 30. Oh, there's 2 of them. That's kind of interesting. Then here's the big tip, 105%. So we are way out here. I'll try to make that one a little bit bigger just so it pops a little more. Then a 19% tip. 10% again. Back in my day, that was considered a good tip, but times have changed. 32.1%. I'll let this one jitter and put it right here. 11.1%. I'll have to jitter that one and put it about here. Finally, last one's 15%. And where's my 15? I'll put it right about here. So we got it, folks. There's our dot plot. And now that we have this dot plot, we're going to do something that's kind of uncomfortable. We need to know its shape as well, and we're used to doing that when we see a histogram. So when you answer this next question, just keep in mind, you can get a shape assessment even off just a dot plot. Any volunteers for what you would say this shape is here?
Probably just this weird, like, bright speed histogram.
Exactly. We tried putting little rectangle shapes on it. Here's where the data is accumulating mainly, and then it skews off to the right. So I absolutely agree. We would consider this right skewed. And how about modes? Would you say it's unimodal, bimodal, or potentially worse? I agree. Unimodal means you have to find where the main peak is, where most of the data accumulates. Looks like it's about right here. Data falls off to the right and to the left. We do have to make a judgment call around here, but it looks like it's just trailing off. And the fact that some of them are stacked could just be more to randomness than anything really accumulating. So I would say, yeah, based off what I see, definitely unimodal. If some people analyze this and said bimodal, I probably would accept that as an answer because it's really hard to tell in dot plots, in all honesty. I think that would have to be a very forgiving question. But I would say here, probably the best assessment is right skewed, unimodal, and we should probably say one additional thing about the shape. Any volunteers for the last thing to say? Yes, there is something crazy way out there, depending on the way you point. There's a massive, massive outlier, right? So at any time we see something like this, it's something we ought mention as well. So let's also say, and a large outlier on the upper end. Now let me highlight that in yellow just to correspond where the point was. Someone tipped 105%. It could be a mistake. Maybe that will be canceled with the credit card company, but for the moment, that's what the data looks like. Any questions at all, folks, with the shape of these data? Yeah, go ahead.
So like when you're seeing outliers at the upper end, because I know like on Instagram, they call it like tails.
Mhm.
On this, is it just the end?
Oh, you could call it upper tail as well, and that would have been fine. Yeah, in fact, I think a lot of times when you write this, you might have said a large outlier at 105%. You can give this specific value as well, and that would have been all right. As long as you mention the outlier, that's probably the major thing I'm looking for as well. Other questions about that so far? Okay, so that's tipping percentages. And now this is really the new question on part C. What summary statistics should we use in order to describe the center? I mean, we're kind of looking at it. Typical values, I'd say 12%, maybe 11%. Well, there's a right skew, so maybe it's more around here for the central value, closer to 15. But if I have to use a statistic, anyone see what the right statistic would be? I agree, it's got to be M, the median for the center, and it's only because we said the data was right skewed. So let's say here, they didn't ask us to explain our answer, but I'll put it here in the parentheses. Since these data are right skewed. And now the nice thing about our table is certain statistics always go together. Let me scroll up just to show. If you use the sample mean, you will be using the sample standard deviation and vice versa. Likewise, if you chose M for the center, we must choose the interquartile range to describe the spread. So these statistics are paired together. In fact, you need one statistic like X bar to calculate the other, like S, for example. Same with interquartile range. So we'll say here, when it comes to variability, we will use IQR. Any questions at all, folks, on either one of those statistics? Okay, well, in a sense, we've pretty much finished it, folks. Section 3.1, Again, our author has some pretty short sections, especially at the start or opening of a chapter. And this is the main takeaway from this section. You'll see various data sets. They could be as a histogram or as a dot plot. And our job is just to say, what statistic do we need to use to actually calculate center and variability? Well, any questions at all then, folks, before we conclude these notes here? Okay, I guess I do have a question. I mean, in the very next section, we will calculate these statistics in section 3.3 and 3.2 for the other set. But I'll leave it up to the class. Should we calculate the statistics right now on these data just for the heck of it? Okay, I have some saying yay. Awesome. Let's give this a try then. Let me first kind of clean this up. Now, when I do data sets in class, especially if it's going to be a timed exam, I keep them short because the last thing we want to do is take too much time keying in data into our calculator. That's not really assessing our understanding to the best. So imagine if it was an exam problem, I would probably cut off the data set to about maybe the first row. Something between 8 and maybe about 15 to 16 would be the most I give you. But this is a fair web assignment problem, and it doesn't make it easy. This can be kind of tricky. The thing that makes all of this very tricky is in WebAssign, we have to put in all the data into the calculator very, very accurately. If we miss one digit up, if we move a decimal point, or if instead of 55.2, I put 52.5, transposing the digits, that's enough to throw off the statistic, and it's enough for WebAssign to tell. So for me, I think the best advice I could give is go slow and you will be saving a load of time. Let me see if I can rearrange these windows just a touch. I'll start putting these in, starting at row 1, working my way down. Another thing you ought to try to do when you do this is count the number of observations. 3, 6, 7, 8. So 16, 17, 18, 19, 20. Yeah, this would be on the upper end. I probably wouldn't give anything more than this amount of data. This is quite a lot. But this is not a bad idea to do in WebAssign. If you have 20 observations, we'll double check that in our calculator to see if we duplicated or missed anything. That's an easy way to miss the problem. Now, the first thing you have to click on your calculator once it's warmed up and ready to go is first the stat key. It brings up this menu right here, and you just hit enter right away. You want to go to edit your data set. So I'll hit enter right here. And now the trouble with this is I have some data already. You could just override them, but sometimes it's best to just clear it out, especially if L1 had like 50 observations. And if I overwrite with just 20, I still have to delete all that stuff anyways. Here's one way to clear out L1 really quick. Go up arrow so that L1's highlighted like you see here. Hit clear. Now notice it says L1 equals, well, nothing, and then we'll just hit enter and it should wipe it out, bringing it back to that display. Does that look right to folks in folks' calculator so far? Okay, awesome. Now, here's the tough part. I'm going to type these in methodically, one at a time. Give it a try yourself, and if you were watching and you see me miss something, let me know. I'll try to correct it. So starting off with a 0, 5, 45, 32.8, 13.9, 10.4. I forget if I'm talking while you're doing this, I'm probably distracting you, so I'll be quiet for a moment. Okay, I should have it here. Next thing I would look at is, once you're done with it, I'm at this blank entry. I'm about to put in the 21th observation, which we won't do because we're done. And that's how I know, yeah, we did put in the 20 observations that we indicated right here. Now, if this was a WebAssign problem, it's not a bad idea to double check these values. But let's just see what happens and let me know if our values are a little bit off. Any questions so far, folks, on the data import? Okay, once you have all your data contained in, it should say L1 right here. Next thing you want to do is hit the stat key. We're nearly done. We'll go over to the tab that says calc to calculate. And we're going to default to one variable statistics. So at this stage, I just hit enter a lot. Let me pause here though. Usually I just hit enter a bunch of times on this screen, and you'll probably be doing the same as you use your calculator more and more. But the very first time you do this, make sure it says L1. Let me move the cursor. It should see L1 right here. Frequency list should be completely blank. And if that's the case, just hit enter while it's flashing on calculate. After we do that, we've produced our statistics that we wanted. But keep in mind, we can't use XBAR, right? XBAR would be at 27.315%. So it's about here. That's where it's going to settle. My prediction when I was looking at it visually, I was first saying about 11, 12%. I was thinking maybe 15%. I could be way off on that. But if 27% is right here for X bar, I can guarantee the median should be to the left of that because we have right skewed data. So let's take a look. Here's the next big trick on the calculator. If you see output that has a down arrow, there's a lot more. Just hit the down arrow a bunch of times. And this is the stuff we actually wanted. I'm going to take a screenshot here so we can see what we grabbed when we wrote out our answer. Forgot there was an example too, but we'll come back to this. So on this problem right here, we can now say that the median, M, is approximately equal to that value right there at 21%. So my guess at 11, 12, maybe 15%, definitely was way off visually. I guess that is the power of having these statistics. We don't have to guess or point on a page. So it was about 21% for there. The average was 27%, which was substantially a lot more. And what about IQR? It's on here, but we just have to write it out. So IQR, by definition, is quartile 3 minus quartile 1. And notice that's exactly what they're giving here. Quartile 1, quartile 3. These are really strange words, and we're going to define them all rigorously. But if you're curious what they mean, the median is sometimes thought of as quartile 2, but it just is not something that's written on the calculator. It's the 50th percentile. Quartile 1, that's the 25th percentile. And quartile 3 is the 75th percentile. Now, what this means is here at quartile 3, 75% of the people who tipped less than 35.6%, and 25% of them tipped more than that value. So that's what makes it a 75th percentile. While as quartile 1 is the 25th percentile. So if we want to actually calculate the interquartile range, here's how it goes on our next step. IQR, putting these in parentheses only because this is extra based off the instructions right here. Well, IQR would be always quartile 3 minus quartile 1. So it'd become 35.6%, our upper quartile, minus 10.75. And now let's go throw that back into the calculator. If you want to calculate and you're stuck on one of these screens, I usually just hit clear to get back to a clean slate. So 35.6 minus 10.75 gives us the value of 24.85%. But we did it, folks. That's the median. That's the interquartile range. Any questions at all in calculating that through the calculator? Okay, and I did forget to ask, sorry about that, but how do these values look? Are folks getting about the same values we see here? Awesome, I'm glad to hear that. So if we go back to this display one last time. Here's what our statistics are finally showing us all together. On this dot plot, it was really pretty hard for me to find the central value. I was looking around here, but because it's right skewed, we absolutely should be using the median. And we said the median is at 21%. So M would go right here at that location. So that's the 50th percentile. Half the dots are to the left, half the dots are to the right at that position. Now, the median is not so bad to understand on a graph, but in my opinion, the interquartile range is a little bit trickier. So that's the major reason I want to show it today. So the interquartile range is the difference of quartile 3 minus quartile 1. Let's plug those on the graph, just get a feel for where they're at. Q1 goes right here, roughly. Quartile 3 is further to the right, 35.6. So here's quartile 3. Right at that location. So what's the interquartile range? It's the distance from, let me put a little dashed lines. So from here to here, the distance between the upper quartile to the lower quartile, that distance is IQR. Recall that we said quartile 1 is the 25th percentile. Quartile 3 is the 75th percentile. And what that means is everyone between this dot to the left and this dot to the right, that's the central 50% of all observations. It's in that way the IQR says how spread out everything is. If that was compressed, if the IQR was say 12, our whole data set is going to compress this way. My IQR was say 30, my data set would expand this way, spreading out all the dots. Well, any questions or comments at all, folks, about any of these measures? Okay, well, let's take a look at maybe one more problem, and we'll start section 3.2 in earnest. Well, we'll see where we end up. I forgot I had an example 2 here, but I believe this one was a little bit shorter. Here we have an actual histogram, and this was an example histogram that I pulled out earlier, just so we could take a look at a histogram. So we're returning to the data reported in the article, synovial fluid, pH, lactate, oxygen, and carbon dioxide, partial pressure in various joint diseases. That takes a lot of oxygen to say, but this is a arthritis and rheumatism journal from 1971. And what I mentioned before, the way they did this is, if you suffer from arthritis, maybe rheumatoid arthritis, you get flare-ups in your joint area, pretend this is my knee. So they have to go in with a pretty large gauge needle into your joint space. I think they call this, there's a word for this, I forget. They take out your joint fluid and that relieves pain if it's too pressurized, or they can analyze it to diagnose your disease. And that's what they did here. We have lots of observations from the knees of individuals suffering from arthritis. And all they were doing with these fluids is measuring how acidic they are on this pH scale. This is more on the basic end. If it was, say, around 5 or lower, it'd be acidic like coffee or worse. So first thing we want to do is describe the shape of this distribution here. And I'll leave it up to the class. What would you say the shape is for this? Symmetric or skewed in a direction? I agree with skewed right on this. If you said roughly symmetric, I think that might be acceptable as well. It's a bit borderline for these data. So sometimes there is more than one acceptable answer I would take if it were an exam question. But because of that feature highlighting in yellow, I do feel skewed right is a good response for this. So you could say positively skewed, you could say skewed to the right, or this is the fastest way to say it, just skewed right. Then as far as modes go, here's the main peak right here. So I would consider these data to be unimodal. But we need to, I think we mentioned it before on these data, be careful with what's highlighted in yellow. The separation is really, really tiny here. This one individual is still close to the main grouping of data. I wouldn't consider this to be an outlier unless it was moved, say, to somewhere over here. That's over there. Now we're looking at a pretty large outlier in that case. If you see just one rectangle separation from an observation to the next, typically that may not be considered an outlier visually. Well, other questions, folks, with the getting the shakedown on these data? Okay, you could add further, no apparent outliers. If you said that there is potentially a borderline slight outlier right here to the right, that would be acceptable as well. But anything that's just purely qualitative like this, as long as you say the things that fit the picture I see here, I'm not going to be too picky on how I grade these. WebAssign is because, I mean, they just have a right answer or a wrong answer that they're coded to select. Well, now that we said skewed right to unimodal, once again, for the summary statistics, the center, we would use the medium M, and for the variability, we would use the interquartile range, IQR. Now it says, briefly explain your choices, but the word right here is almost a hint when I say briefly. It means you really don't have to say very much. I would say here, since these data are skewed. Any questions, folks, on getting through this one? Awesome. Well, this one's kind of nice because we have a histogram. It's a lot easier to determine shape for those kinds of data rather than building our own dot plot. But what we'll be doing next in section 3.2 is we're going to turn towards distributions that are really just symmetric, calculate the summary statistics for those, see how they work, and do the same for distributions that are just skewed. So those are our next two sections we're going to take a look at. Let me save this up. And any last questions, folks, before we turn to the next set? Okay, I'm not going to try to take all of your time today. We're back from a holiday, for goodness sake. So let's open it up and see if we can just get started. Our author has a habit of writing really, really long titles. I don't think that's a bad thing, but I do think it's impressive. So when you go to WebAssign, I actually can't type that out. There's a limit to how long I can make the section titles. So occasionally things are abridged. Just look for the number particularly. 3.2, I'd probably just say center and variability for symmetric. So the way these notes start is, first, we have to get on the same page for notation. When I say X, the variable of interest, think of like in just the last problem, the variable of interest was pH for the joint tissue. X is going to refer to just a typical observation. We use this right here a number of times. Whenever you see a lowercase n, we're just saying how much data you have, the sample size of the data set. And anything like this, and x1 is going to be the first observation, and x2 would be the second observation, and so on. So that's the way our notation is going to work. Let me see if I can grab some actual data. So for example, in this problem, 3 would be x1, that's the first value, 10 would be x2, and so on, all the way to the very last one. And if there's 15 observations, we would say n equals 15. So we'll see these values all over the place. Now finally, here's how we define a couple interesting statistics. The sample mean is through this formula. We add up all the observations, and then we just divide by the sample size, number of observations in the sample. So writing it out in words, that's kind of nice. If you had to write it out as a mathematical formula, it would look like this to start. First observation plus the second observation. The dots are just saying, and so on until you get to the final observation, xn. So if we were back to this problem, the numerator right here would just be taking 3 plus 10 plus 5 plus 5, so on, all the way to xn, add the 6. Then just divide by the size of the data, the number of observations, and you have your sample mean. We've made the calculator do it a couple times. And when it comes to statistics, certain things are just written so often, like that right there, that we have shortcuts for that. The shorthand symbol for repeated addition of different values will look like this. It's the summation symbol. It's an uppercase sigma if you're curious and care about the Greek letters there. But think of this as summation, which is just a fancy way of saying add everything up. So my formula right here, it's saying add everything up in the numerator, then divide by n. Does that make sense to folks running through that formula? Okay, for me, this is a kind of a nice formula. It has an actual physical interpretation that we'll be taking a look at. And here's where it gets really, really weird. The sample variance. Already, there's some interesting things happening. Notice when we calculate the mean, you divide by n, right? If you calculate the variance, you absolutely do not divide by n. You divide by n minus 1. To me, that's really, really odd. And there is mathematical reasons for this. If you're curious on why we divide by n minus 1, I could give you a couple thoughts on that. One reason is when you go to calculate the sample variance, take a look that x bar is actually part of that formula. That's a little bit weird already, right? Variance is based off the sample mean. It's the deviation of your values from the central value, the sample mean. Now, here's another thing that's kind of wild. If I take one value, any one value from the data set, whether it's x1, xn, and just totally delete it, as long as you know what the sample mean is, and you know all the other observations, you can actually solve for that and bring it right back. What we say here is there is n minus 1 degrees of freedom, because if I'm missing just one data value, and I know the sample mean, I can actually bring it right back. That's not so much an explanation, it's more just talking through it, right? If you're curious on more rigorous reason of why n minus 1, I encourage you to take a look at this video right here. I lost it. There it is. That's just a really, I think it's a 6-minute YouTube video that shows a little bit more graphics, a little bit more math, and a condensed explanation of why divide by n minus 1. It's completely optional, so if you skip it, that's okay with me. But let me show you the way that this really is going to affect us a lot. That n minus 1 also emerges right here, where it causes some trouble in the sample standard deviation. Now, when you go to your calculator, let me turn this on. I'm just going to go and read you a computation we just did. So here's my statistics. Here's the biggest thing to worry about in the calculator. If you use that value, sigma x, what has happened is you divide by n, not n minus 1, and it turns out that value is wrong. This can happen in Excel too, by the way. If you're doing standard deviations in Excel, you have to be very, very careful on what value you pick. You have to pick SX. That's the sample standard deviation, which will use n minus 1 here in the variance and here in the standard deviation. So here's what the difference is. If I have 15 observations and I used sigma, what I am saying is those 15 individuals is the population. But if those 15 individuals is just a sample of a larger population, you use SX, not the sigma x. So that's the big difference between the two. Well, we only got as far as looking at the formulas. Any questions or comments, folks, then, before we call it a day? Okay, when we come back next class, we're going to do a deeper dive into this, and we'll see how to calculate stuff by hand in this table down below. This is just to understand the formula, and then we'll rely on the calculator as we go forward. Well, have a great night, folks. Sorry, I thought I was going to end a little bit earlier, but it's not 6:50 yet, so we did end early.